Hi everybody and welcome everybody once again to another installment of our series of Discovery seminar talks. I am Matilde Mingozzi, a Space Telescope postdoc, and today I will be the chair. The aim of the Discovery seminars is to showcase the work of postdocs of the Space Telescope and Johns Hopkins community. As you know, early career researchers have been disproportionately affected by COVID-19 pandemic due to reduced travels and networking opportunities. And on top of that, we have here at Space Telescope a large community of international postdocs. So with these talks that will take place till the end of July, we want to provide a platform for them to show their results to an international audience of astronomers. Please, at the end of each talk, feel free to ask questions using the raise hand button, and I will call on you, and then you can unmute yourself to speak, or you can type questions in the chat also during the talk, and I will read them for you at the end of the talk. With further ado, I will introduce our first speaker today. Our first speaker is Nicole Arulanantham. She has been a Giacconi Fellow at Space Telescope since September 2020 and works to understand how ultraviolet light from young stars influences chemistry in protoplanetary disks. She completed her PhD in 2020 at the University of Colorado Boulder as part of the Colorado Ultraviolet Spectroscopy program, and in her free time she enjoys being outside and reading. Nicole, the floor is yours. You can share your screen. I cannot hear you. You are muted.
Can you hear me now?
Yes.
Okay, perfect. Thank you so much for having me. I'm really excited to show you all some of these results. So we'll be taking a look at some spectra from Hubble's ULLYSES program, where the acronym stands for the Ultraviolet Legacy Library of Young Stars as Essential Standards. And so I'm really excited to show you these new spectra. Now, I'll be talking a lot about Lyman alpha photons and T Tauri stars today, and so I wanted to start by showing this schematic from Lee Hartman's 2016 paper. And I'll reference this throughout the talk, and I'll pull it up again just so we can see the different components of the environment that we're looking at. So this shows what we expect the environment around a typical T Tauri star to look like. So this sphere over here represents our star. Now the T Tauri stars are young, low-mass stars, so these all have masses smaller than 2 solar masses. And I'll be talking about systems that are between 1 and 10 million years. Okay. So this category includes what we think are the young precursors of Sun-like stars. So that's why we're particularly interested in this category. Now, as we move to the right in the diagram, we see these kind of red loopy lines here, which represent the magnetic field lines generated by the star. The T Tauri stars are actively accreting, so they're pulling material from the gas and dust disk along these field lines and onto the star. And when the material crashes onto the stellar surface, it produces this very hot, dense accretion shock region. And so the ultraviolet continuum emission and line emission is produced in this region where we have accretion flows and the accretion shock. This is also actually where the optical continuum and line emission is generated, and we have X-rays coming from here as well. Then as we continue to move to the right in the diagram, we reach the protoplanetary disk that surrounds the star. So here we're looking at kind of an edge-on slice through the disk. So the very center here is where we have the disk midplane. So this is where we expect conditions to be cool and dense enough for protoplanets to be forming. And as we move up away from the midplane, we see the disk get puffier, and so this is where we have a gaseous molecular layer. Now, each region of this environment can be observed at a different wavelength, and so the very hot central region we can observe with the Hubble Space Telescope. As we move further away to material that is still warm but not quite as hot as the central region, we can observe these components with JWST and previously with Spitzer and Herschel. And finally, as we go to the coldest, most outermost regions of the disks, we can observe these at submillimeter wavelengths with ALMA. So today I'm going to talk a lot about these Lyman alpha photons generated at the accretion shock and in those flows. And here is an example of a typical Lyman alpha emission line observed from a T Tauri star with the cosmic origin spectrograph. So here we're looking at the flux on the y-axis, and the emission line is in velocity space along the x-axis. And so line center at 1215 angstroms is right at velocity equals 0. Now, the first thing you might notice about this emission line is that there is a flat missing region in the middle. And this is because the cosmic origin spectrograph is effectively slitless. And so we get a lot of geocoronal emission that comes into the aperture and kind of blocks off the low velocity Lyman alpha emission. But you'll also notice that the Lyman alpha emission from T Tauri stars is very broad. So on average, these emission lines are about 800 kilometers per second at the full width half max. And they also contain a lot of flux. So when we compare the line fluxes from Lyman alpha to the rest of the UV radiation field, we find that on average, the Lyman alpha makes up about 88% of the total T Tauri star radiation field. And we know that these UV photons have a very strong impact on the chemistry in the protoplanetary disks, which in turn influences the composition of planets that form in these environments. So it's really important to characterize the Lyman alpha emission so we can get a better sense of the chemical evolution of the protoplanetary disks. One thing I forgot to mention, I know it can be a little difficult to follow along with virtual talks, and so at the top of each slide, I've just put a sentence with the main takeaway from the slide. So if you get lost at any point, just read this sentence and then hopefully you'll be looped back in and ready to go. Okay, so the Lyman alpha is very important, and so if we can understand what it's doing, we can get a better sense of how chemistry happens in protoplanetary disks. We have some very nice models of how we think Lyman alpha should interact with molecules and disks. So this figure shows some simulations from Catherine Walsh's 2015 paper. And in each of these 6 panels, we're looking at the height above the disk midplane on the y-axis. So our T Tauri star would be somewhere here off near the origin of the plot. And then we're looking at distance from the central star along the x-axis. So here we're looking at the innermost regions of the disk that we would observe with JWST. The bottom 3 panels here are showing column densities of HCN molecules in the disk, and the top row is showing C2H2 molecules. And both of these species can be photodissociated by Lyman alpha photons. Now, the 2 panels on the left-hand side are the column densities shown in the disk around an M dwarf. So M dwarfs are very low mass stars, and we expect them to have reduced UV radiation fields and Lyman alpha emission compared to disks around Herbig stars, which we're looking at in the far right. Herbig stars are the most massive young stars, and so the disks around them will receive the strongest UV radiation fields. And in the middle, we have our T Tauri star. And so in all of these plots, we can see a dark regions here corresponding to peaks in the abundances of these molecules. And we can see that in both the M dwarf and the T Tauri disk, we have C2H2 and HCN that are able to exist above the disk midplane, whereas in the Herbig disk, the molecules have to live very close to the midplane where they're shielded from the Lyman alpha photons. And these 2 molecules are particularly important because they tell us about the nitrogen and carbon carriers in the protoplanetary disks. So when we look at these simulations, we see these very nice, clean predictions. But when we go to look at the data, the picture is a little bit more complicated. And so we really want to characterize these Lyman alpha profiles that we observe so that we can better understand what we're seeing in the data from JWST in the future and current observations with ALMA. So the Lyman alpha emission lines that were observed with the cosmic origin spectrograph have previously been modeled by Matthew McJunkin. And so he fit these models with a very broad initial Gaussian emission line, which is shown here as this blue dashed profile. And then he superimposed Voigt absorption lines onto these Gaussian emission lines to represent absorption from atomic hydrogen in the disk environment and also in the ISM along the line of sight. But an issue that Matt ran into was that half of the line profiles on the blue side of the emission lines were very difficult to fit, and so he focused his models on the red side of the line profiles. So if we zoom in on some of his results, we can see the data shown here in black, and the orange curves in each of these panels shows the best fit models. And so we can see that they do a decent job of fitting the red side of the line profiles with some exceptions like the high velocity emission and BP tau. And so this provided some really nice constraints on the column densities of intervening H1. But it turns out that the blue sides of the Lyman alpha profiles also can carry a lot of information. And so if we quantify the shapes of the line profiles, we can measure the shape by integrating all the flux on the positive velocity red sides of the emission lines and divide that by the integrated flux on the blue sides of the emission lines. And we can plot this against a tracer of dust in the protoplanetary disk, and we see this very strong linear correlation. So on the x-axis here, we're looking at that flux ratio of red to blue Lyman alpha emission. And on the y-axis, we're looking at the infrared spectral index. So this tells us the relative proportion of emission at 13 microns compared to 31 microns, which translates in physical space to emission from smaller warm grains relative to cooler large grains. So if we look at our disk cartoon, this would be comparing emission from grains kind of in this region of the disk to grains in kind of this region of the disk. And so when we have more emission from the cooler large grains, we get very large values of the infrared spectral index. And this is attributed to the smaller grains either having grown to larger sizes or being removed from the disk in dusty disk winds. And so we can see that in disks that have less of this 13 micron emission, we also have more emission on the blue side of the Lyman alpha emission line than on the red side. And so if we add some other tracers of the protoplanetary disks to this picture of Lyman alpha, we see what appears to be an evolutionary sequence. So in the top row here, we have these outflow dominant targets with outflow dominated P Cygni like Lyman alpha emission lines. And these targets, when we look at them at submillimeter wavelengths, so with ALMA or the SMA, we see very smooth distributions of dust. So we don't really see any gaps or rings or spiral arms, but we do see very strong signatures of jets and outflows that would include H1 in the outflows. Then we have a whole subset of targets that sit kind of in the middle of the plot that have roughly even levels of red and blue Lyman alpha emission. And then finally, we have our targets that have inverse P Cygni Lyman alpha emission lines. And these targets all have very prominent, very large dust cavities. And so this combined with the shape of the Lyman alpha profiles might be indicating that these targets are in the last stages of rapidly dispersing their inner disks. So we have accretion onto the central star, kind of absorbing the photons on the red side of the emission line. So this is material moving away from us along the line of sight, removing photons on the red side. Okay, so we have this nice tentative picture of Lyman alpha and disk evolution, but you might recall from the plot I showed you on the previous slide that this is not very many targets, right? There's maybe a dozen targets on this plot. And so thanks to the ULLYSES program, we can build a much bigger data set and start exploring this connection between the Lyman alpha profiles and the disk kinematics in a much larger data set. So this plot is showing the measured ratios of red to blue Lyman alpha flux for 44 T Tauri stars that are included in the first 3 data releases of the ULYSSES program. Now, all of these spectra are publicly available. The data is reduced and processed by an excellent team here at STScI, and they have some really nice visuals and some very cool data products that you can download at ulysses.stsci.edu. And so when we look at these 44 targets, their names are just on the x-axis and they're plotted in order of increasing Lyman alpha flux ratio. We can see that the data now span 3 orders of magnitude, and they're pretty well sampled until we get up to this kind of very large flux ratio range. One thing that immediately jumps out from this plot is that about 70% of the targets sit in this regime with more red than blue Lyman alpha flux, which corresponds to P Cygni-like or outflow suppressed emission lines. And just 30% have these inverse P Cygni profiles where infalling material is suppressing the photons on the red side of the lines. So right away, this is kind of consistent with our picture of late-stage inner disk dispersal, because since we see fewer targets in this infall suppressed category, this is consistent with it being an evolutionary stage that happens very quickly. So we don't expect to see very many targets here because it happens so fast. So we have all of these nice spectra, and we want to fit them with more comprehensive models that might tell us a little bit more about what's going on in this disk environment than the previous Gaussian and Voigt absorption models. And so my colleague, Max Gronke, who was a Hubble Fellow at JHU and now is a scientist at MPA in Germany, has these very nice Lyman alpha models that include scattering. So this will account for photons that are scattering through the disk wind and jet region and through the protoplanetary disks. And so in Max's model, we can imagine that we're now looking at our T Tauri star and disk system from the top down. And we start with a central source of Lyman alpha photons. So this would correspond to the T Tauri star accretion shock and accretion flows. And the Lyman alpha source is surrounded by a shell of H1 that will absorb the photons and scatter them. And so this would correspond to the disk wind and jet, and also the material in the accretion flows that's falling onto the stars. So if the shell is expanding away from us, that would be analogous to material being dispersed from the protoplanetary disk in a wind or jet. And if the shell is shrinking, that would correspond to material that's accreting onto the star. So Max fit his scattering models to all 44 of the targets that I showed you in the previous slide. And for comparison, I fit our simple Gaussian emission and Voigt absorption model to the full Lyman alpha profiles and the same targets. And this is a comparison of the model fits. So on the left-hand side, we are looking at the best fit model to the spectrum, the ULYSSES spectra from RY loop, when scattering is included. And on the right-hand side, we're looking at the same data fit with the model when scattering is not included. And so we can see right away that the model that includes scattering does a much, much better job of fitting the full Lyman alpha profile, especially on the blue side of the line where the Voigt absorption kind of forces the model to sit below where we see data on the blue side of the line profile. So what this means is that the models that the model parameters that we extract from these scattering models will be more robustly constrained and will be more reliable tracers of what is happening in this inner disk and accretion shock environment. Now, in order to actually learn something from these model parameters, we want to see which ones are most closely correlated with the shapes of the Lyman alpha emission line profiles, which we know are tracing this kind of sequence of disk evolution. So in this figure on the y-axis, we're looking at the ratios of red to blue Lyman alpha flux. And on the x-axis, we're looking at the velocity of that shell of H1. And so positive velocities here are actually the shell moving inward. So these are the accretion-dominated profiles. And the more negative velocities are the profiles that are dominated by outflow and jet absorption. And so the points, the blue circles, are showing the best fit model parameters from the models where scattering wasn't included. And the cyan squares are showing the values from when scattering was included. And we can see actually that the velocities are pretty consistent across the two modeling frameworks. And we see this very tight correlation between the velocities and the ratios of red to blue Lyman alpha flux. So we know that the velocities will be a nice tracer. But it turns out that it doesn't seem to matter how much H1 is doing the scattering or absorbing. Again, we're seeing the ratio of red to blue Lyman alpha flux on the y-axis here, and the best fit model column densities on the x-axis, with the blue circles showing the models where scattering isn't included, and the cyan squares showing when scattering is included. But there's no real correlation here. We do see a couple of targets that have very low column densities in the scattering models, but these are both systems that have very large dust cavities in their circumstellar disks, so it makes sense that the scattering models would return lower column densities. And the Lyman alpha flux ratios also don't seem to depend on the widths of the initial emission lines generated at the accretion shocks. So again, we're looking at the ratios of flux on the y-axis and the best fit model full width half maxes along the x-axis. And the full width half max does not really seem to be tracing the final shape of the Lyman alpha profiles that we observe. Okay, awesome. So we have a model parameter that is very robustly tracing the sequence of evolution. And just as a check, we want to see whether this can be attributed to the angle at which we're viewing the circumstellar disks. So if we come back to our schematic, we can see that if we're looking at the disk edge on, like we're looking in this cartoon, any Lyman alpha photons generated at the accretion shock and in the accretion flows would have to scatter through the disk wind and jet and the protoplanetary disk in order to get to us. Whereas if we were looking at the system from the top down, we might see photons that have to travel through the accretion flows, but may have to traverse less of the disk wind and jet and the protoplanetary disk. And so it turns out, actually, that we don't see a correlation between these model H1 velocities and the disk inclinations. Now you'll notice that this plot is more sparse than the previous figures we looked at. And this is just because these are the most robustly constrained disk inclinations. Some of the ULLYSES targets are rather faint and haven't been observed with ALMA just as yet. But what we can tell from this plot is that since there aren't correlations between the velocities and the disk inclinations, these velocities are actually tracing physical processes happening in the disks as opposed to just the geometry at which we're viewing the systems. Now, the region that we want to learn more about, right, is this very hot inner gas disk and the base of this wind and jet launching region. But we can see from this figure that this sits kind of right in the middle of where we would be able to observe this with HST and with upcoming observations with Webb. And so, as a complement to the ULLYSES survey, Carlo Manara at ESO has put together the Penelope program. I don't know if I had to remind myself of the Greek mythology, but Penelope was chosen very specifically to represent Ulysses, or Odysseus's wife. So the Penelope program has acquired spectra with the VLT instruments from near UV to near infrared wavelengths for all of the ULLYSES targets, as close to simultaneously as possible. And we can use the K-band spectra from the Penelope program to measure the amount of inner disk veiling. So this is how much emission from the inner disk fills in the spectral features from the central T Tauri star. And when we compare the veiling measurements to our model velocities, we see this very nice, clean correlation. And so the smaller K-band values correspond to less emission from the inner disk, and these infall-dominated inverse P Cygni Lyman alpha profiles, whereas larger values correspond to more inner disk emission and outflow-dominated Lyman alpha profiles. Now you'll notice that we have some targets that are kind of hanging out here by themselves. So it turns out that the more active accretors, or the targets with larger inner disk excesses, are much harder to measure veiling. And so our team is currently using a few different methods to measure the veiling, and then we will compare the differences as a function of accretion rate and try to get a much more statistically robust relationship here. So you can imagine that the linear relationship will be very tight in this region, but we'll have much more uncertainty as we move to systems with stronger inner disk emission. And finally, just to bring it back to thinking about the molecules in the disks, now that we know that the Lyman alpha emission changes as a function of how much stuff is left in the inner disk, we can go back and see how the molecules we observe with JWST and ALMA change as the inner disk dissipates. And so these are two Lyman alpha profiles from targets that are in those late stages of inner disk dissipation. And the dotted lines here mark off transitions that are able to dissociate HCN molecules. And so I'll have a student starting this summer who will think about how the differences in these HCN transitions might translate to the observed molecule distributions. And just lastly, really quick, I want to draw your attention to the larger collaborations that are working on some of the ULLYSES data. So first we have Odysseus, which stands for Outflows and Disks Around Young Stars, Synergies for the Exploration of ULLYSES Spectra. And our team put its first paper out in early 2022. There should be another one coming from Kaylee Pittman, who is a grad student up at Boston University in the next couple of months. And then finally, again, we have the Penelope program led by Carlo Manara at ESO. And the first two Penelope papers are available as well. They were published late last year. One is just presenting an overview of the main survey, and the second one is diving into one particular target that is a close binary. So that is everything I wanted to show you. Thank you for listening, and I'll be very happy to answer any questions.
Thank you very much, Nicole, for the very beautiful talk. Let's see if there are questions in the chat. If you have a question, you can raise your hand going into the people panel on the right in blue jeans and click on the raise hand button, or you can just type your question in the chat and I will read it for you.
Is there a question in the library?
Oh, sorry, I didn't see you.
I'm using the raise hand feature.
You can ask your question.
Can you hear me okay?
Yeah,
out there?
I can hear you.
Okay, I was using the raise hand feature I was born with. This is Jason Tomlinson in the library. Nice talk, Nicole. You showed that there wasn't a huge difference in the velocities you get when you turned the scattering on and off, which suggests the optical depth isn't huge in the region that's doing the Lyman alpha emission. And that would seem to support your argument that you're looking at the kinematics of the flow rather than internal process. Is that right?
Yes, yeah. So what is tricky about the velocity, so there are also still very large error bars there. What's tricky is that the geocoronal emission is kind of preventing us from seeing, when we look at H alpha emission lines from the T Tauri stars, for example, we sometimes see multiple absorption components, and so we're missing that with the Lyman alpha.
Okay.
But the fact that the velocities that we're getting from the two different modeling frameworks are so consistent does seem to tell us that we're tracing something real and physical within the system, as opposed to just kind of loosely fitting models that are returning something that we can't understand.
Okay, thanks.
Thank you. And we have a question from Leonardo dos Santos. You can unmute yourself and ask your question.
Yeah, sorry for interrupting before. I just found the raise hand feature on the iPad, which is not. Anyway, my question is, I got curious about the Lyman alpha modeling. Nicole, I don't know if you have all the details, but do you know what assumptions they make for the intrinsic Lyman alpha emission of the host star? Do they have like a first principles modeling of that, or do they just assume something for the intrinsic emission? Do you know about that?
So we can't actually see the intrinsic emission from the host stars. So with the T Tauri stars, they're accreting so strongly that the emission lines are kind of dominated by what we see at the accretion shock. Now, the ULLYSES program does include some very weakly accreting T Tauri stars, and so it seems that as the systems stop accreting, the emission lines get narrower and narrower, and so you lose kind of the very high velocity, broad components of the emission. But it turns out some of the people who have been using the weak T Tauri stars as modeling templates to represent the stellar contribution have actually been having a very hard time using them. So it appears that the weak T Tauri stars are not actually so weak. So basically, we assume it looks from the weak T Tauri stars that the Lyman alpha just shrinks in width and intensity. But that's about all we know. So in the models, the assumption is just a Gaussian that can match that can eventually either by scattering, increasing the broadening, or intrinsically can capture those broad wings.
Thank you very much, Leo, for the question, and thank you very much, Nicole, for the talk. Now we have to move to the second talk of today, but if you have further questions for Nicole, she has her office here in Rotunda, or you can send her an email, so please reach her. So the second speaker of today is Emily Rickman. Emily has been a European Space Agency Research Fellow here at Space Telescope since September 2020. She works on combining various exoplanet detection techniques to characterize precise dynamical masses and atmospheres of exoplanets and brown dwarfs. She completed her PhD at the University of Geneva in 2020, where she also held a short postdoctoral position, and she completed her master's across both the University of Sheffield and the Australian National University. So please, Emily, share your screen, and the floor is yours.
Okay, let me just... All right, can you hear me and can you see the correct screen?
Yeah.
Okay, great. Yeah, thank you so much for the introduction. I'm going to talk today all about different exoplanet detection techniques, especially in the context of directly imaging exoplanets and what we can learn from combining all of these different exoplanet detection techniques. So before I jump into that, I just wanted to outline some of the main motivators of why we might care about these different exoplanet detection techniques, especially for direct imaging, which probes very widely separated exoplanets and brown dwarfs. So first of all, we don't really understand what the occurrence rate of long period exoplanets, brown dwarfs, and even low mass stellar companions really looks like. When I say long period, I'm talking about things more than 5 AU away from their host star. And so understanding the occurrence rate is really key in helping us understand actually how these objects form and also how these objects evolve. On top of all of this, by actually detecting and characterizing these long period exoplanets and brown dwarfs, we can start to understand what the mass luminosity age relation of these companions look like, especially as we get an age estimate from the primary star that we're looking at, and we get precise dynamical masses, which I'm going to talk about in detail during this talk. And on top of all of this, a really great benefit of doing direct imaging of exoplanets is we're able to probe some of the atmospheric features that we see using integral field spectrographs, and we can get those of both giant gaseous planets and also brown dwarfs, which act as really great analogs for those giant gaseous planets. So I want to get everyone on the same page of what different exoplanet detection techniques I'm talking about. So first of all, the radial velocity technique, which some of you may be familiar with, but it's okay if you're not. I'm going to talk about it now. So in the radial velocity technique, we have a primary star, which is shown by the yellow circle here in the center, and then we have some companion that's orbiting around that star. So that could be an exoplanet or a brown dwarf, shown by the blue circle there. And as they orbit around their center of mass, the central star, the host star, gets tugged in various directions due to this orbital motion. But we know what the spectral lines of the host star look like, which is shown in the bottom right panel there. And as the star gets Doppler shifted towards us and away from us, those spectral lines get shifted to the left and to the right, red and blue shifted. So from this, we can measure the speed at which this happens. So that's the velocity of the radial direction, and that's what's showing in the right-hand plot there. And we also get an idea of how long it takes the companion to orbit around its host star, i.e. the orbital period. I'm also interested in astrometry, which is another indirect detection technique. And it's similar in the way of radial velocities in that we're measuring the effect that the companion has on the host star that we're observing, but rather than talking about the radial direction, we're talking about the spatial direction. So in astrometry, we observe the path of a star across the sky over several years, and this creates a linear path across the sky as it moves through the galaxy. And we also see the spiral motion, which is just simply from the motion of Earth moving around the sun. But the thing that we're really interested in are any perturbations from the expected astrometry of a star that we observe, which is shown here by that brown-orange color. And those perturbations on the sky can be caused by a companion that is orbiting around the star that we're observing that could be an exoplanet or a brown dwarf or a stellar companion. And the third and final technique that I'm primarily interested in is that of direct imaging, which luckily is pretty easy to explain because it does what it says on the tin. But what we do is we look at stars that may have a planet or a companion around it. And if we're interested in ground-based observations, which sometimes we are, then we have to account for the Earth's atmosphere, which is shown here by that fan causing that turbulence. And we have to correct for this using what's called adaptive optics. But imagine a pair of glasses that's moving at frequencies of tens of thousands of times a second to correct for a perturbed wavefront entering the telescope. But the really important thing for direct imaging for both ground-based and space-based observations is what's called a coronagraph, represented by the thumb of the person taking a photo in this representation here. And what that does is suppresses as much of the primary starlight as possible, because that's not what we're interested in. We're interested in finding those point spread function point sources that are orbiting around the star itself, and then that's fed into a detector. So if you're only going to take one thing away from this talk today, then it's the next couple of slides that I'm going to show you. So I'm a huge advocate for combining different exoplanet detection techniques. Think of this like baking a cake. We need different components. We need the eggs, the flour, the sugar, the butter, to bring all these components together to make a delicious cake. But what's happening at the moment in exoplanet science is we're taking one detection technique and saying, hey, this is a great cake, or hey, we understand what this exoplanet is doing, just from one technique alone, which may be extremely model dependent, which is certainly the case for direct imaging. What we need to do is bring all of these components together so that we end up with that delicious cake that everyone wants to eat, or a well understood exoplanet, where we remove a lot of the degeneracy of unknown orbital parameters, so like the orbital inclination, for example, which gives us a well-rounded understanding of the exoplanet that we're looking at. One of the key things about combining these different techniques as well is not just understanding the exoplanets themselves better, but also probing this diagram that I'm showing here. So this is just a plot of all of the detected exoplanets to date, taken from the NASA Exoplanet Archive. We've just reached over 4,000 detections now, and we have the semi-major axis on the x-axis there, so that's kind of like a proxy for the orbital period, or how long it takes the planet to orbit around its star, and then we have the mass on the y-axis. And you can see that the different techniques that I've plotted here, the kind of main ones that we're interested in, but I'm going to hone in on the ones that I'm particularly interested in, so that being the radial velocity technique that I mentioned before, particularly the long period radial velocities that may present candidates that are amenable to direct imaging, because we want candidates that are far enough away from their star that are not hidden within the bright stellar flux. And then also these directly imaged candidates that I spoke about as well. And what's happening over time, bearing in mind exoplanets is a relatively young field, is as we're observing radial velocities for longer and longer periods of time, we start to probe outwards in terms of the semi-major axis we're able to access with radial velocities alone. And on the imaging side, as we start to go to bigger telescopes with better angular resolution, as well as smaller inner working angles and more sophisticated instrumentation and post-processing techniques, we start to probe inwards on the semi-major axis, and also down to more extreme contrast ratios, so those smaller and smaller masses, and we start to bridge these exoplanet detection techniques together over time, which is a really powerful tool in understanding what we're looking at. On top of all of this, we'll place the sort of expected mass separation parameter space, where we expect astrometry to start filling in some of the gaps of this as well, particularly with ESA's Gaia on the sky, and still with upcoming data releases, will really start to become a powerful technique. And as we can see there, overlaps a lot with the radial velocity and imaged planets that I'm talking about as well. So let me bring all of this together. So we have the radial velocities, and these provide an estimate of the orbital period of the thing we're looking at, as well as the minimum mass of the companion that we're interested in, bearing in mind we don't know the orbital inclination if we only have the radial velocities. Then we include the astrometry in this, and this removes that degeneracy of the unknown orbital inclination, which reveals a dynamical or model-independent mass of the companions that we're looking at. And this is really powerful in obtaining precise dynamical masses of the thing we're looking at, which enables us to compare against models. And indirect imaging also allows us to add in relative astrometry, which again gives us that precise dynamical mass estimate, and obtains spectral information using integral field spectrographs in order to test the models of the atmospheric and evolutionary models. And so together, all of these things provide a comprehensive characterization of the things that we're looking at. So I have been using the ULLYSES survey, which provides radial velocities, along with Hipparcos and Gaia data, which are the ESA satellites that are measuring astrometry of stars, as well as using SPHERE on the VLT to carry out direct imaging of some of these candidates. So let me start by introducing the ULLYSES survey, which is an ongoing radial velocity survey for more than 20 years now. It contains more than 1,600 main sequence, primarily G and K dwarfs, and it's a volume-limited sample within 50 parsecs, so really within the solar neighborhood. And within these radial velocities, I've been looking for long-term drifts hosting potential companion candidates that could be amenable to direct imaging. So in 2019, I published a paper of some of these long-period radial velocity candidates that I've highlighted here, back on that same mass separation parameter space diagram that I showed you before. And as you can see, these really sit at the bridge between those extremely long period radial velocity planets that could seep into the ones that are potentially detectable using direct imaging. One of the things we can do as well, by combining radial velocities with the astrometry, is actually predict where we expect the position of the companion to be with respect to the main star that we're looking at. So I show here, this is done using an orbital fit with a package called Elvira from Brantatel 2021. And we have the delta ascension on the x-axis and the delta declination on the y-axis of how far away, or the projected angular separation of where the companion would be with respect to the main stellar host. So we can use this precursor information from radial velocities and astrometry to predict this position and to see if we actually expect to be able to detect this object using direct imaging. So for the ones that are particularly promising, I went forward and imaged a bunch of these with SPHERE on the VLT. And so for those of you not familiar, we can access two components of the instrument simultaneously. So we have narrowband imaging using ERDIS, which is an infrared dual band imager and spectrograph. And that's across the Y, J, H, and K bands. And then we also have the integral field spectrograph, or the IFS, which allows us to obtain a low resolution spectra of the object that we're looking at. So one of the promising objects that I pulled out from my 2019 paper was HD 13724b. And again, I'll emphasize that this radial velocity data is more than 20 years worth of data. So these radial velocities are really large. And we found that it was at least had a minimum mass of 27 Jupiter masses, so at least a low mass brown dwarf. So we went forward to image this with SPHERE, and what I show here are images from both 2018 and 2019 where we have this is spectral differential imaging, and the white circle in the middle is where where the coronagraph sits that I mentioned before, to remove as much of that primary starlight as possible. So the primary star sits behind that circle. And then we see that we can actually see the companion there across those three images in the H, J, and K bands. So combining this radial velocity information that I showed on the previous slide with the relative astrometry that we obtain from direct imaging, so that's the separation and the position angle of the images, we obtain more of a sort of mid-mass brown dwarf of around 50 Jupiter masses. At this point, we sort of remove the model dependency that we typically have for direct imaging, and are able to obtain a pretty precise dynamical mass from doing this. So now we have a model-independent mass. This is really key in order to compare against atmospheric properties of the object that we're looking at. So here I show the spectrum of this object. So we have the IFS data, which is the integral field spectrograph, highlighted in pink there. And then we have the narrow bands highlighted in the gray bands there across the J, H, and K bands that I showed from the previous images. And we make comparisons against some field brown dwarfs as well as atmospheric models, and at which we see some nice strong absorption features from methane and water vapor there. And from this comparison with the models, we find for it to be a spectral type of about T4 and a temperature of about 1000 Kelvin. So it's in pretty good agreement with the models that we see, but this is really key in making sure that the models we're looking at make sense. So then in 2021, Brandt et al. Went forward to combine even more information folded into this particular target. So before I had the relative astrometry from direct imaging and the radial velocities from the Correlate survey. They then folded in absolute astrometric accelerations from Hipparchus and Gaia and found it to be about 36 Jupiter masses and honed in on the precision of that dynamical mass. And in this paper, which is a really interesting paper in general, I encourage you to go and check it out if you're interested, is that younger and lower mass brown dwarfs are actually overluminous compared to their models, while older or higher mass brown dwarfs are underluminous. And this is really key in us actually obtaining these precise dynamical mass to test these kind of theories. So there are a number of companions for which I've been carrying out these imaging campaigns. And so I am just about to submit this paper on a handful of actually very low mass stellar companions within this Correlate sample. And so what I show here is the contrast ratio between, on the y-axis, between the primary stellar host as well as the secondary stellar companion that we're looking at, and then the projected separation in the sky in arc seconds on the x-axis. And we can assess the detection probability that I mentioned before. And so these are just a bunch of stacked contrast curves, 5 sigma contrast curves from on-sky performance from SPHERE. And the lighter colors correspond to we are quite likely or very likely to be able to directly observe these things, and the darker colors correspond to that we're unlikely to. So in this case, you can see that these are all relatively massive companions compared to those lower mass exoplanets and low mass brown dwarfs. So these are all relatively easy to image using SPHERE. But these are really key in helping us understand what the occurrence rate of these objects looks like. So from this, we were able to directly image a whole zoo of these stellar companions, and which I show here, including one triple system, which was interesting to discover as well. I'm not going to go through each of these systems in detail, but I did want to highlight a couple of cases, which I think emphasizes the point of this talk. So for HD 92987, which I actually initially published in 2019, I actually published a mass of about 17 Jupiter masses, and this was from the radial velocities alone, which you can see in the right-hand plot there. So from that, we interpreted that as either a very low mass brown dwarf or a very massive giant planet. But then going forward in 2021, Venner et al. Folded in the absolute astrometric accelerations from Hipparchus and Gaia and found that this object is actually a very low mass stellar companion of about 250 Jupiter masses. I actually went on to image this companion, which I showed on the previous slide, of one of our directly imaged companions, and found that we were able to obtain a complete model-independent mass of about 260 Jupiter masses. So very much in agreement with Venner et al. Once we folded in the relative astrometry from imaging, and we find that it's almost on a face-on orbit. So the plot on the left there shows the orbital fit by combining all of this information together, and we see that it's almost that the inclination of it is almost at 180 degrees. I think it's about 176 degrees. And I feel like this is a bit of a cautionary tale of when we publish radial velocity detections in exoplanetary science, which is a very common thing to do, is that we take the minimum mass that we publish to be the actual mass of the object. So in this case, if we just kept in the radial velocity mass that we obtained of 17 Jupiter masses, then we would assume that it was either a very giant planet or a very low mass brown dwarf, when in fact it's very much a star. And this can play into how we understand the occurrence rate of these objects. And so any exoplanetary scientists in the audience should take away this cautionary tale when we talk about the occurrence rate of objects if we don't have the known dynamical mass of the thing that we're talking about. I also wanted to highlight this particular companion just because it's so eccentric, and I thought the radial velocities looked really neat. The HD 143616, we have the radial velocities on the right there, which we can see is extremely eccentric, and it's actually going through its periastron passage around 2020, and luckily we were able to sample that pretty well as it was happening. And then by combining, again, the relative astrometry from direct imaging with absolute astrometry from Hipparchus and Gaia and the radial velocities, again, we find this as a low mass stellar companion of about 280 Jupiter masses and an eccentricity of 0.97, which I think is pretty insane. So pulling this all together, we can compare mass luminosity relations. In this particular case, I'm showing the parsec mass luminosity relations for very low mass stars, where we have the mass on the x-axis and the H-band magnitude that we obtain on the y-axis. And we put a comparison against all of the companions in this particular paper, and we find that their dynamical masses agree fairly well, although we do note that for HIP 22059, we actually find for it to be underluminous for its given dynamical mass. And this can be explained by having an unresolved binary companion that is orbiting the B part of the companion itself, so it could be another brown dwarf counterpart that we haven't resolved in our data, for example. And we're still assessing why we find the HD 157338 is slightly overluminous for its given dynamical mass. But these are really important in helping us calibrate these mass luminosity relations that we obtain by using these precise dynamical masses. So going forward, we start to probe down to smaller and smaller masses, and I show here the direct detection of two brown dwarf companions that I'm hoping to publish soon as well. And from these, we have very neat orbital fits, again from combining their radial velocities, which I show on the two left panels for each one, and their orbital fits by combining all of this data together. And we find for these two particular ones that they're actually brown dwarf companions that sit right at the border of what is considered a stellar or a substellar companion. So I think these are really key in probing that sort of blurred line between what's considered a star and what's considered a brown dwarf. And we're also going to pull out the atmospheric information of those particular objects to really study those in detail. So stay tuned for that later this year. Okay, so going even further ahead, we have James Webb Space Telescope, recently launched, extremely exciting here at Space Telescope, of course. And this is really going to enable us to probe down to those exoplanetary masses using direct imaging. So with NIRCam, with NIRSpec, with MIRI, is really going to enable us to do this. Aaron Carter did a really great study in 2020 of what kind of detection space we may be able to obtain, where we have, again, the semi-major axis on the x-axis there and the mass of the companions that we may be able to directly image. And we expect to be able to get down to sub-Jupiter masses or even sub-Saturn masses beyond 50 AU. So that's going to be really exciting. And one of the key points in this is all of this work I presented today really acts as precursor information in order to select the most amenable targets for direct imaging with JWST. And so with that, I will pull up my final conclusions and state that this work really does help us understand the occurrence rate of the objects I'm talking about. So both exoplanets and brown dwarfs and even low mass stars, especially within the solar neighborhood around nearby solar type stars. And these objects really help us populate the mass luminosity relation for these kind of companions. The precursor observations are really going to be necessary in increasing the detection efficiency of high contrast imaging of exoplanets. especially with expensive telescope time with JWST, and in the future when we get the ELTs come online and any kind of future LaVoie Habex style flagship mission that will be probing direct imaging of exoplanets, we cannot afford to spend time blindly looking for exoplanets in the hope that we find something. We need to use this information to understand the object that we're looking at. And I think the main takeaway point from all of this is that combining these exoplanet detection techniques is extremely vital in being able to comprehensively characterize the exoplanets and obtain those precise dynamical masses and their atmospheric properties. And with that, I'll thank you for listening, and I'm happy to take any questions.
Thank you, Emily. Really interesting talk. And I loved the animation, especially of the cake at the beginning. Let's see if there are questions. I don't see something in the chat. I don't see. There is a question in the library.
Thank you, Mark. Hi, Emily, very nice talk. Congratulations. I also love the cake. I wonder if you could comment on how do you expect the new Gaia data release to affect your estimations for the masses?
Yeah, so I think the Gaia data release that's about to come out soon, that's DR3, I think will just help us verify the astrometric solutions of the planets or companions that we already have. I think a big game changer is going to be Gaia DR4, which will be in the next sort of couple of years. And that will probe like a different sort of separation space I'm talking about. So it will be shorter orbital periods because you'll look at the acceleration between like Gaia DR1 and Gaia DR4. And so you can kind of probe a smaller sort of inner working angle rather than combining with Hipparchus, which has like a 25-year baseline between the Hipparchus observations and the Gaia ones. So the next data release will be really great in verification, and then the following data release from that will be really great in probing a different separation space.
Great, thank you. I see that there is a question from Nicole.
Hey, so I really liked your images with the J, H, and K band images right next to each other. And it looks like in the K band there's consistently a lot more speckling around the, I guess, where the star is blocked off. Does that cause problems with, I guess, characterizing the planets? And is there a point where the K band gets so contaminated that it's not helpful anymore?
Yeah, that's a really interesting question, actually. Yeah, so we get more sort of background emission in the K band just from being at a longer wavelength. It becomes a lot noisier, and it's especially an issue with ground-based observations. So it definitely is important to cover as much of the different spectral bands that we can in order to make sure that the thing we're looking at makes sense. In the K band as well, I actually had a program looking at gravity data, which is an interferometer which probes mid-resolution K-band spectra, which is going to really help us hone in and understand what we're looking at in the K-band once we put that together with spheres. So that's a really great question in terms of understanding that. I guess I didn't say it in the talk, but we do see a slight flux excess in the K-band, and we believe that may be due to some cloud coverage that we're not completely compensating for, like in the models. So the K-band is definitely like the sort of most uncertain of the bands that we look at, and that's why it's really key to obtain that mid-resolution to high resolution, especially with instruments like gravity. But that's really sort of expensive telescope time in terms of 4 times 8.2 meter telescopes. But yeah, so hopefully that will help us understand even better what we're looking at in the K-band.
Is there, sorry, a quick follow-up question.
Yeah, no worries.
Is there anything to be gained in terms of, would this be cloud coverage in Earth's atmosphere?
No, sorry, I should have specified in the atmosphere of the companion that we're looking at. So you probe certain silicates at that wavelength that you don't probe at other wavelengths. And so there's still uncertainty in the atmospheric models that we look at in terms of really properly taking this into account, especially for different spectral types of brown dwarfs and giant planets. And that's why it's really important to do this to help us understand that.
Okay, Cool, thanks.
Thanks, Nicole.
Thank you, Nicole, for the questions. I see that that Leonardo dos Santos has still the hands up, but I'm not sure if it was from before. So I think that there are no more questions for today, and also we reached the top of the hour. So I want to thank the speakers of today again, and for the beautiful talks, and see you for the next. See you in a few weeks for the next Discovery seminar. Thank you, everybody.